Buenos Aires, midnight. The city is breathing. Every movement is a clue, a whisper in the dark. For centuries, we have tried to decipher its code, but the rules of the game remain a mystery. It is a complex system. Along centuries, we have tried to predict its next move, but the rules are a mystery. The first detectives, Newton and Leibniz, wrote the fundamental law of change. This equation described how a system evolves over time. It was precise and elegant, but it had a fatal problem. You had to know the exact rule of change, the function, from the start. If the problem has a description with not many parameters, the old rule usually works perfect. But complex systems usually need too many parameters to be modeled. And here lies the problem. Then a case arrived that broke the books, a silent virus. The classical models failed because the function was unknown. All we had were contradictory, late, and confusing clues. Survey data, internet searches, and reports. An epidemiologist explained in the New York Times, "Tell me the numbers to put in my equations, and I will tell you the answer. But you cannot tell me, because nobody knows them." And here we had again the problem with the old ways of modeling. But now people were dying with this unpredictable killer. But then, in the dark alleys of mathematics, statistics, physics, and computer science, a new breed of investigators emerged, the infamous neural networks. They didn't follow the rules. They found them, capable of approximating any complex function if fed enough clues. The super detective combines the old law and the new methods. The neural network replaces the unknown function, learning the system's dynamics directly from the clues. The system learns its own dynamics. This approach is continuous, flexible, and way more powerful if you have the data. The virus continued spreading. A case report was filed. It used the whispers of the pandemic for predicting where the virus would be next. The official reports were late. Crucial clues were in the whispers of the people, captured through massive daily Facebook surveys. The 5 key clues included early and late indicators, like symptoms and doctor visits, admission to hospitals, new reported cases. The detective interrogated the clues from the whispers. The brand new neural differential equation learned the hidden dynamic connecting the whispers to the virus's spread. The result was successful. An accurate prediction of new cases up to 60 days in advance. This could allow to design policies for saving people's lives. But then an unexpected twist. It's not a crime, it's a conspiracy. The virus outbreaks were not isolated. One city infected another, and traffic in one street affected the dynamics next door. The dynamics were interconnected, interwoven in an invisible network, like a graph. The challenge was modeling the entire network, not just a single system. An old mathematics structure was proposed, the graph. For a crime of this scale, a new type of detective was needed, the graph neural ordinary differential equation. This model understands not only the temporal dynamics of each node, but also how spatial connections influence that dynamic. It models continuous evolution across time and space if combined with a new kind of neural network, the graph neural network. This new instruments that combine the classic differential equations with graph theory and machine learning, the graph neural networks are versatile. They act as an encoder, mapping initial clues to a latent representation, as the differential equation, modeling the continuous flow of states, and as a decoder, interpreting the latent trajectory into a processable conclusion. The method that can crack the virus spread doesn't stop here. The same logic applies to any complex dynamic system where interactions are the main feature. It can be applied to simulate physical systems, material science, for traffic forecasting, recommendation systems, and generating new graphs for drug discovery. The journey began in the dark streets of an uncertain city. It led us through a torrent of digital clues to the mind of a new detective, and, finally, to the conspiracy that connects everything. The code of dynamical systems has been broken. The hidden dynamics of climate, finance, and biology are no longer an insoluble mystery. The detective have a new set of tools that, with data, can solve many new cases. This work is based on the research work titled Forecasting Virus Outbreaks with Social Media Data via Neural Ordinary Differential Equations by Matias Núñez from CONICET, Nadia Barrero from INVAP, both from Argentina, Rafael Barrio from UNAM from Mexico, and Chris Rakakis from MIT, published in Nature Scientific Reports in 2023. Idea and Direction by Matias Núñez. Music by Hugo Diaz.